Welcome to Gradient Canvas. Today we're going to learn about what really happens inside a single call to model.fit in XGBoost, every step, from the raw data to the finished ensemble of trees. Here's a line of code you've probably written 100 times. Model.fit XY. You press enter, a progress bar ticks, and a few seconds later you have a trained XGBoost model. But what actually happened in those few seconds? Because behind that one innocent line, XGBoost just built hundreds of decision trees, one after another, each one carefully computed to fix the mistakes of the ones before it, using gradients, a regularized objective, and a closed-form formula for every leaf. In this video, we're going to open up that single function call and watch step by step everything fit does. No hand-waving. By the end, every argument you pass to that model will mean something concrete. First, what does fit receive? Two things. Big X, your feature matrix, one row per example, one column per feature, age, income, clicks, whatever describes each case, and little y, the target, the single number or label you want to predict for each row. Fit's job is to find a function, call it capital F, that takes a row of features and outputs a good prediction of its target. And here's a detail people miss. Fit doesn't hand you back a new model. It trains the object in place. When it finishes, the fitted trees live inside the very same model variable you called it on. Everything from here on is about how XGBoost searches for that function f. The very first thing Fit does is not build a tree, it reorganizes your data. XGBoost doesn't work directly on your raw array, it packs it into its own internal structure, a DMatrix. And crucially, for each continuous feature, it bins the values. Instead of keeping thousands of distinct ages, it buckets them into a fixed number of ranges, by default up to 256 bins, controlled by the max bin setting. Why? Because when it later searches for the best place to split, it only has to consider a couple hundred candidate thresholds per feature instead of every single unique value. That one decision, bin once, up front, is a big part of why XGBoost is so fast. This binning happens exactly once before the loop, and every tree reuses it. Now the loop is about to begin, but every loop needs a starting point. Before a single tree exists, XGBoost makes one constant prediction for everything. This is the base score, and you can think of it as the model's best guess with zero knowledge. For regression, essentially the average of the target. For classification, the overall base rate expressed as log odds. So our function f starts life as a flat line, the same number for every input. It's obviously wrong for most points, and that's completely fine. That gap between the truth and this starting guess is exactly what the first tree is going to attack. Here's the engine room, the step that repeats every round. At the start of a round, we have the current prediction f for every point. XGBoost now asks for each point two questions about the loss function. First, which direction and how hard should this prediction move to reduce the loss? That's the gradient little g, the first derivative of the loss with respect to the prediction. For squared error loss, it works out to simply prediction minus truth, the signed error. Second, how curved is the loss right here? How quickly does that gradient itself change? That's the Hessian little h, the second derivative. Ordinary gradient boosting uses only the gradient. XGBoost's signature move is to use both, a second-order Newton-style step. So every point now carries a pair g and h, and that pair is the entire instruction set the next tree receives. So what precisely is the new tree trying to optimize? XGBoost approximates the loss around the current prediction with a second-order Taylor expansion, and that's exactly why it needed both g and h. For one tree, the objective becomes a tidy sum over all points. G times the tree's output plus 1/2 h times that output squared, plus a penalty on the tree's own complexity, written omega. That penalty is XGBoost's discipline. It has two knobs. Gamma charges a fixed price for every leaf the tree adds, and lambda, an L2 penalty, pulls every leaf value gently towards zero, so no single correction gets too bold. So Fit isn't just reducing error, it's reducing error minus a fee for complexity. That built-in regularization is a big reason XGBoost resists overfitting where plain boosting struggles. Now XGBoost grows the tree, one split at a time. Sitting at a node with a bunch of points, it asks, is it worth splitting here, and where? For any candidate split, it adds up the gradients and the Hessians on each side. Call the sums big G and big H, left and right. Then it plugs them into the gain formula. Intuitively, gain measures how much the regularized objective improves if we split, versus leaving the node whole. A score built from G squared over H plus lambda on the left, plus the same on the right, minus the same term for the unsplit node, and finally minus gamma. And remember those bins from step 1. For each feature, it just sweeps its couple hundred histogram buckets, accumulating G and H, to find the split with the highest gain, fast, because it's counting bins, not sorting raw values. The best split across all features wins the node. Fit won't let a tree grow forever. Several guardrails cut it off. First, max depth caps how tall the tree gets. Second, look again at that gain formula. It subtracts gamma. If the best possible split can't clear that gamma toll, the gain comes out negative, and XGBoost simply refuses to split. That's pruning, driven by the gamma you set. Third, min-child weight demands a minimum total Hessian in each child, loosely, enough evidence, or the split is rejected. And one more elegant detail. What about missing values? For every split, XGBoost also learns a default direction. It tries sending all the missing valued points left, then right, and keeps whichever gives more gain. So missing data isn't imputed or dropped. The tree learns where to route it. This is called sparsity-aware split finding, and you get it for free. Once the tree's shape is fixed, every leaf needs an output value, the actual number it will contribute. And here's the payoff of setting this all up as an optimization. We don't search for the leaf value, we solve for it. Minimizing that regularized objective for a single leaf gives a clean closed form. The leaf's weight is the negative sum of the gradients in it, divided by the sum of the Hessians plus lambda. Negative big G over big H plus lambda. And look at what lambda does there. It sits in the denominator, so a larger lambda shrinks every leaf value towards 0. That's the L2 regularization made concrete. No iterative fitting inside the leaf, one formula, computed directly from the G's and H's that landed there. The tree is built, its leaves are filled. Now XGBoost adds it to the running model, but not at full strength. It multiplies the entire tree by the learning rate, ETA, a small number like 0.1 or 0.3. So the update is new f equals old f plus ETA times this tree. Why hobble every tree on purpose? Because small steps generalize. If each tree could fully correct the errors, the first few would overfit wildly, and later trees would have nothing stable left to do. Shrinking each contribution means many modest trees each nudge the prediction a little, and the ensemble lands somewhere much smoother. There's a direct trade-off you'll feel in practice. A smaller learning rate usually needs more trees, more rounds, to reach the same quality of fit. Before we loop back around, 2 more dials shape what each tree even gets to see. Subsample lets each tree train on only a random fraction of the rows, say 80%, a different random slice every round. And colsample by tree does the same for columns, handing each tree only a random subset of the features. This isn't laziness, it's deliberate regularization borrowed from random forests. By showing every tree a slightly different view of the data, you stop the ensemble from leaning too hard on any one pattern or any one feature, and you reduce the correlation between trees. As a bonus, training on less data each round is simply faster. So even inside a strictly sequential booster, a controlled dose of randomness makes the final model more robust. Now zoom out and watch the whole loop turn. Compute G and H, grow a tree, fill its leaves, shrink it, add it, then recompute G and H against the new, slightly better prediction, and go again. How many times? By default, exactly n estimator's rounds, 1 tree per round. But there's a smarter way to stop. If you hand-fit an evaluation set, eval set, it scores the model on that held-out data after every round. Pair that with early stopping rounds and fit will halt as soon as the validation score stops improving for that many rounds in a row, keeping the best point instead of grinding through trees that only overfit. So the number of trees you actually get can be fewer than you asked for, decided by the data, not just by the setting. When the loop ends, what do you actually have? Fit has stored inside your model object the whole ordered list of trees, the trained booster. Nothing else changed. The same variable now simply contains the machine. And prediction is the mirror image of training. To score a new row, start from the base score, drop the row down every tree, following those learned splits, and the default direction whenever a value is missing, collect the leaf value it lands in, multiply each tree by the same learning rate, and add them all up. For regression, that sum is the prediction. For classification, you pass it through a sigmoid or softmax to get probabilities. That's the entire model. A base score plus a sum of small shrunken trees. Everything Fit did was decide carefully what each of those trees should say. So let's replay model.fit in one breath. Bin the features once into a DMatrix. Start from a constant base score, then, each round, compute every point's gradient and Hessian. Grow one small tree whose splits maximize the regularized gain. Prune anything that doesn't clear gamma. Give each leaf the value -g over h plus lambda. Shrink the whole tree by the learning rate, and add it, repeating until the rounds run out or validation stops improving. And every argument you pass now has a home. N estimators is the number of rounds. Learning rate is the shrink. Max depth, gamma, and min child weight shape each tree. Lambda regularizes the leaves. Subsample and colsample add the randomness. That one line of code is this entire disciplined loop. Next time you call it, you'll know exactly what it's doing. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please like, subscribe, and share it with others. Join us to explore more AI concepts from neural networks to transformers. See you in the next video.